Hi, my name is Neha Dasani, and this is Physics Lab Report 4. So first, I will be giving an introduction on the fundamental physics principles, going over the experiment and assumptions, going over the observed model, the results, the tracker code, the final results, which include the graphs, the errors, and the what-ifs. So for the key concepts used, we have the magnetic force on a wire loop, which is the cross product of the current I and length along with B, the Newton's third law, which is force is equal to the opposite and equal of the magnetic force, and Ohm's law, which is V is equal to IR. So as you can see in these equations, we have the magnetic force is IL cross B. We have the force of B, the magnetic force, is equal to I times 2 pi RB, and this is another version. We have I is equal to V over R, which is also V equals IR, which is Ohm's law, and then V is equal to M, which is equal to the derivative, the negative derivative. So for the experiment, I will collect observational data of the magnet falling through a conductive tube of aluminum foil. I will model the magnet tube interaction computationally, and I will compare my computational predictions with my observed data. So for the observed model, we have the system, which is the falling magnet, and the surroundings, which is the aluminum foil tube and the earth. And this is a picture of Faraday's law. So for my observational results, I did 5 trials and I found the average time. I also found the length of the tube, the width of the foil, the inner radius of the foil tube, the total radius, and the mass of the magnet, and the magnetic dipole from lab 3, I believe. And so I found that the average time from these 5 trials is 0.69 seconds. So for my tracker code, I had to input the values like mu over pi, resistivity, G, the geometry of the tube, which includes the length, the width, the inner radius, and the outer radius. And then on this second image, I had to input the magnitude of the magnetic dipole moment, which I found was 1.5. And then they gave me a value to use, which is 2.166, which I will use to get 2 different graphs. And you will see this in the further slides. Then I had to calculate the d flux over dt. I had to find the bar position. I had to calculate the magnetic force of the tube on the magnet. And then I had to apply Newton's second law towards the end of this picture where I did bar dot vel is equal to bar dot vel plus F net over mass times delta T. And then this shows me a graph with time. So as you can see on the left is the graph that I used with my magnetic dipole moment from lab 3. And on the right is the graph that gives me when I use the magnetic dipole moment that is given to me using 2.166. So the magnetic dipole moment from lab 3 gave me 0.308 seconds. And when the magnetic moment dipole was used, I got 0.345 seconds. So as you can see, these values do not match each other or the average value I got, which was 0.69 seconds. So given the given magnetic moment dipole may be closer to the actual value because when using the given magnetic moment dipole, I got 0.345 seconds and the average time is 0.69 seconds. So this is closest to each other. So some possible errors in this lab are that there may have been friction between the magnet and the tube. The magnet makes contact with the tube as it travels down the aluminum foil. There may have been human error due to measurement when using the stopwatch, and there may have been human error when measuring the dimensions of the radius and the length of the aluminum foil tube. So for the first what if question about what if the resistivity of the conductor were reduced as close as possible to 0 and how would the dynamics change? So resistivity is directly proportional to the resistance, so there would nearly be 0 resistance. There would be greater magnetic damping. The increased opposing magnetic force significantly slows the magnet's descent. And the magnet may fall very slowly or even achieve near levitation. The magnetic force balances gravity. Now, what if holes or slots were cut into the tube and how would this affect the ring's currents? So this would interrupt the continuous current paths and lead to redistribution around the holes. The field distribution, this would modify the electric and magnetic fields. This would influence the current distribution. There would be increased resistance and localized heating around the edges, causing potential power losses. And this may alter the tube's inductance and capacitance, and this may impact the overall current behavior. Thank you.